We'll just record it, I'll edit it in.
Okay, great.
Okay, so good morning everybody. My name is Philippe Gauzet from the University of Liège in Belgium, and I am chairing this first session on multiferroelectricity. I would like to thank Ron for the nice introduction and for all the organizers for pursuing this tradition of ferro workshops, which I like very much. So the first talk of this session will be, it's an invited talk. It will be given by Karin Rabe from Rutgers, and the title is Competing Phase in Transition Metal Oxides, Ferroelectricity and Antiferroelectricity from First Principles. Karin.
Oh, shoot. No. Okay.
Did you just touch something?
I touched my thing. Let's see.
Okay. Uh-oh.
Can we start? I'll start while you fix that. So it's really a pleasure to be here, and I'm glad everybody could make it to this meeting today. I'll be talking about first principles work on competing phases and functional properties. I'm Karin Rabe, and the work that I'll be showing you was done at Rutgers with many members of my former and current members of my group who are listed here, and a number of them are giving talks at the meeting, so I'll foreshadow that a bit as well. Okay, now this thing is not working. Hopefully it'll kick in at some point. Okay. Now this is frozen. The only way I can, okay. Okay, we'll see how that works out. So as Ron said, this is the 30th workshop on the fundamental physics of ferroelectrics. Back in the early 90s, we were talking about perovskites, and we're still talking about perovskites because perovskites are so interesting and so exhibit such incredible variety and richness of behavior. So, we have as our parent phase, high symmetry parent phase, the cubic perovskite structure. It's got, inherent structural frustration expressed by the tolerance factor. And one of the ways of relieving the structural frustration is through an unstable polar mode that shown here that is responsible for generating ferroelectricity and barium titanate and lead titanate. And in these early days, we were doing first principles calculations, and understood that by calculating the zone center phonons in the cubic structure, we could identify this unstable polar mode, which we would then freeze in to get the double well potential for the ferroelectric. Now, that's not the only instability. There are many perovskites have many other kinds of lattice instabilities, which are listed here. And one really beautiful way of kind of getting a handle on those instabilities is to map the full phonon dispersion relation of the parent structure from first principles. And so this is just an example where we look at calcium titanate, which has the polar instability at gamma, but also oxygen octahedron rotation instabilities at M and R. Here I'm just, they're pulling one from the literature. And to get the low energy structures, you combine one or more of these unstable modes, freeze them in, and see what you get. So in calcium titanate, you could get nonpolar PBNM from the rotations, or polar R3C from a combination of rotations in the polar mode. Of course, now we also have come to realize over the years that if you have open shell transition metals, you have many other kinds of orderings that are possible in these systems, magnetic, charge, and orbital, and those also couple to the lattice modes. So you have spin-phonon coupling, where by changing the spin order from antiferromagnetic to ferromagnetic, you can actually induce in polar instability in europium titanate and strontium magnetite, making ferromagnetic ferroelectrics. And then there are other kinds, again, this is not comprehensive, but I just mentioned that you have orbital ordering non-Teller-induced ferroelectricity in superlattices. We work from the group of Philippe Gauzet. So we've got lots of ways of getting low energy structures, and then we can tune by external field stress and composition, because these different instabilities couple to these external control parameters differently. to favor one or the other and induce stabilized non-bulk phases. In particular, since I'm interested in the functional properties, the way that I think about this is we have kind of two stages: a static tuning where we adjust some of these control parameters to get to a point where we have two or more competing phases, and then we can do some kind of dynamic tuning, usually like by applied field, where you can tune back and forth across one phase, from one phase to the other, and change the properties. And that's the source of functional behavior from competing phases. So in this talk, I'm going to kind of take that momentum from the past 30 years and look ahead to see how we're expanding our horizons for investigating systems with complex energy landscapes and competing phases where we can find interesting functional behavior. I'm going to, one way of expanding is to recognize that as much as we love perovskites, there are other, there are other parent phases out there, and we want to start systematically identifying them and exploring the functional properties of those classes of materials. And then we're also recognizing that in addition to the soft polar mode, we're building up a whole repertoire of mechanisms for generating polar phases that compete with each, that can be the ground state or compete with nonpolar phases and antiferroelectrics, and that these are not just lattice modes, but include the electron spin and electronic degrees of freedom as well. So again, this is kind of, I'm going to talk about some of the ways we've been developing first principles strategies to explore these complex energy landscapes and identify these competing phases, because these energy landscapes are really, really complex. And I'm going to argue that, in the course of doing this, that we also recognize that there are many different types of ferroelectrics and antiferroelectric behaviors, and argue that zirconia and related compounds are exhibiting this new type of ferroelectricity. Okay, so again, I'm going to I know this is familiar to most of you, but just to, again, since this is the first talk in the meeting and we're all waking up, I'm going to just remind you that, if we're searching for polar phases, almost, we found that a very useful starting point is to look at the first principles phonon dispersion of the parent structure. And so here's an example where they're going to look at a different parent structure. This is honeycomb layers. This is ABC, honeycomb layers of two atoms with a third atom stuffed beneath. Here we're looking at the side to see the layers, because this high symmetry hexagonal structure, which has inversion symmetry, is prone to a distortion where the layers buckle in this polar way, giving this ferroelectric structure. And if you compute the phonon dispersion of this high symmetry parent structure, you'll see an unstable TO mode that corresponds to this buckling. This is a hyperferroelectric, so the LO mode is unstable also. You can read about that in this paper. Even if you don't have a polar mode, an unstable polar mode in the phonon dispersion, if you have a very low frequency polar mode, then you have a possibility to get a polar phase that way by doing some kind of tuning. And that classic example for that is epitaxial strain-induced ferroelectricity with strontium tightening. So here I'm just showing as a function of epitaxial strain, we have the nonpolar phase, and then for compressive and tensile strain, we see that the polar phase becomes that the mode becomes unstable, and we get a polar phase. This is seen both in first principles and experiment. When you're looking at the first principles phonon dispersion relation and you don't see an unstable mode in gamma or soft mode, all is not lost, because you might have other instabilities in the high symmetry parent structure, nonpolar instabilities that actually can be used to produce a polar phase. And this is like, through a higher order coupling to the polar mode. And so I could be having, here I have a third power of this unstable K3 mode coupling to the polar mode. And this is, the well-known property of, this is improper ferroelectricity. And here I'm showing the phonon dispersion relation for the parent structure of yttrium manganite. And you can play this game, we've learned that you can play this game in a more elaborate way. You could have two, or I guess more, unstable modes that are nonpolar that combine together through a higher order coupling, such as a trilinear to the polar mode, to get hybrid improper ferroelectricity. And you can see that in superlattices. It's also in these 327 Ruddleston copper compounds. And I would say that improper ferroelectrics really are different from soft mode ferroelectrics. They behave differently in electric fields and switching, because the energy scale for the distortion is set by the unstable zone boundary mode and not by the size of the polarization. You can see they're often less sensitive to depolarization field effects. Okay, let's continue, continuing along that line. If I look at the first principles phonon dispersion of the parent phase and I see multiple unstable branches, in some ways that's good because there's probably polar phases in there. They're a little harder, they might be a little harder to find, but here this is an example of where we have lead zirconate, where we have multiple unstable branches in the cubic phase. And what we see there is that, yes, we can generate low energy polar phases, but there's going to be a lot more competition with other phases as well, but also more involvement of other kinds of distortions even in the polar phase. So in lead zirconate, the polar structure that you see, which is induced by electric field, is the R3C phase, which has both the polar instability and the oxygen octahedron rotation. And that competes with this complex antipolar PBA on ground state that everybody is so weird, but is yet so familiar. Bismuth ferrite, this bismuth ferrite is very similar. It's got here the polar R3C. It is the ground state, and it competes with a PBNM structure, which is generated by oxygen octahedron rotations. And you can access this structure in bismuth ferrite either by substituting on the bismuth site or by putting bismuth ferrite in the superlattice. So I'm going to foreshadow talks by Colin Heikes, who I'm not sure is here yet, and John Benini, who is here later in the workshop. And this kind of competition where we have polar states competing with nonpolar states is the defining concept of antiferroelectricity. And this has, I've been trying to promote interest in antiferroelectrics. I think that in some ways the functional properties of antiferroelectrics are more interesting than even of ferroelectrics, because we have this electric field-induced transition between two distinct phases. And so instead of just changing from up to down, you can change properties like the band gap or the volume, and other things which are is not something that you're switching in a ferroelectric case. And you can definitely, it's definitely true that also there are relatively few antiferroelectric materials known, and that's always a good situation if you are interested in searching for new examples. Okay, let's see. Okay, moving along. So let's, okay, so that all looks very good, and I'm not saying we can, we should definitely keep pushing ahead on that program of using the phonon dispersion as a guide to help us navigate the energy landscape. But it's also true that we need to, that is not necessarily going to tell us everything that we want to know. And so now I'm going to talk about how we can search for polar phases not using phonon dispersion relations. And the, and again, there are many, we can start thinking about many ways to do that. One avenue that we've pursued is to use the crystallographic database, ICSD, where we have, a real treasure trove of information derived from experimental synthesis and structure determination about the kinds of structures that different stoichiometries can take on. So our strategy, another way we can look for polar phases is look for polar, and specifically look for polar phases that are, distortions of high symmetry structures and therefore potentially switchable, is to search ICSD for structures with a given stoichiometry and look for a high symmetry parent. And this is, I'm not saying this is a new strategy, this is something that Sid Abrahams, a kind of approach that Sid Abrahams was pursuing already in the 1980s, but it's somehow still, every time we go back, we seem still to find something new. So I think this is a good approach. So in fact, this is, historically, I showed you the hexagonal ABC ferroelectric structure, the parent phase and the polar phase. This is how we, identified these ABC hexagonal systems as ferroelectrics and antiferroelectrics through exactly this kind of search, where we searched on the ABC composition, found these three structure types, and we're like, whoa, these are related to each other by, this is a polar version, this is the an antipolar version. If this is lower in energy, it's antiferroelectric. If this is lower in energy, it's ferroelectric. So that is, so that was one success of this kind of approach. And again, for this very important idea of looking for new high symmetry parent structures. We did this for the composition AB2 also. This is with my student Sebastian Reyes-Lilo, who's now a professor in Chile. And we discovered ferroelectricity in hafnia and zirconia. Unfortunately, our investigation after this discovery revealed that people just at that point were starting to observe this experimentally. So we identified the same structure, triad, high symmetry fluorite structure, a lower symmetry nonpolar tetragonal structure, and a polar orthorhombic structure. And in thin film form, I'm just going to show the zirconia antiferroelectric double hysteresis loop was being observed in thin films. Okay, so that's, I still count that as kind of a success in the philosophy though. But there's one really different thing about zirconia. So the ABC compound fit into this idea that once we identified the parent structure, we could see the polar phase in the phonon dispersion. In hafnia and zirconia, there's like really no, I would say there's no trace of the polar phase in the fluorite, in the phonon dispersion of the fluorite structure. So this is the phonon dispersion of the fluorite structure. This unstable mode here is at the X point. There's like no unstable mode. This instability generates the nonpolar tetragonal phase. And if you go to the nonpolar tetragonal phase and you compute the phonons there, everything's stable. Okay, so there's no, there's no guide here to take us to the polar structure.